Now we are sending the stream. It's running now, right? Is it? Tells me very good connection. The video is off, is it? I don't see any video signal. Do you see something? It looks black to me here. It shouldn't look black. It should be like this sides, you know? A bit boring to try to just wait for live stream. Ah, there we go. So I assume it's working now, right? Maybe. Doing something? Maybe, right? Let me check. So far, so good? Okay, so while we have eye on the stream, I continue because it's quite simple what we try to do. A linear fit. Right? And linear equation, you know all very well. It's y. Oh, very good. So stream is working now. Restarting the software. Right. The linear equation is given here. Y equal n plus x. N is the shift, and m is the inclination. So what we can do, we shift everything to our starting point and x null. Determine at x null the inclination. Well, the inclination is actually the same everywhere because it's a linear function, but still using the given data points, and then shift it up by y naught. So we have made use of the 2 points to fully determine my linear function. Now, this linear function is, however, only valid between those given points. If I have a different set of different points, I need to choose a different linear function based on those points. So here we go. Inclination triangle, we have x, we have the shift, x to x null. Okay. Now, when we have more data available, right, we still could get our data points to that unknown function, that is our measurement, have 5 measurements, and provide estimates of the function values between my data points through the linearly interpolated data. So far, so good? Does this function look very accurate? Well, depends. If the relation is linear, yes, between some data points, it looks fairly accurate. If it looks more like having a curvature, when there could be, depending on my spacing between the data points, quite a big difference between interpolated data and actual relation. Right, also note that we have a piecewise interpolation function, or interpolated function, depending on where you are with your nouns and grammar and adjectives, right? Okay, participles, I guess. So here we have 1, 2, 3, 4 segments. Do you know what's a segment? Segment might be a difficult English word, but segment means like it's a piece of the whole thing. Like, you know what's a cake? Done, go. Right? If you cut a cake for you and your friend, you segment your cake. Good. So here we have 4 segments. Define data points. I prefer to have the notation as smaller x smaller equal x, but you in principle can also have smaller equals everywhere. Just that then some points are defined for two function pieces. Okay, so here we have the picture of our segmented function definition, or the piecewise function definition. And note that each function has a particular region, a segment, where that function is valid. Easy, right? The idea is pretty easy. Now, how do we do this? In principle, we can write a for loop and do this in like 4 lines of code. Right? It's just looping over the data and then defining the function piecewise. No problem. Now, smart people already developed this capability in SciPy, and it's through the interp, so interpolation methods. But I here should say class, right? Because class should come with some functionality. So here's a simplified syntax. So we import interp from SciPy, and it takes 3 arguments. Interpolated function, the one with a dense sampling. XP and FX are the given data points. Okay, so what do we do? So given data points, we simulate again. Here are 6 data points between 0 and 1. We provide measurements at the square root of 1 minus x squared. Then we provide x squared, and we provide interpolated data. So let's see. So we define an X array with NumPy array range, and we have an interp data where we give the actual array where we want to have the data, and our determined are defined here line 7 and 8. So the only difference is once I sample very sparsely means with large distances between the points. And once I sample very densely means very short distances between the points. Good. Execute. Does it work? No, we need to import. We need to run XP. Very good. So what do we see? Well, first of all, this plot could be improved by providing X labels. Second, we see the ideal curve blue. We see the data points given, right? It should be like 6 data points. Let's count. 1, 2, 3, 4, 5, 6. Okay, everything works. Then we have the piecewise linear function. This is our interpolation. And the interpolation connects now the data points, the red ones, right? And we see that between 1 and 0.8 on this to the function are very large. It's not so obvious at the other points, but there it's really large. So far, so good? Yes, right? It's not that hard. Good. Next, we can go to polynomials for interpolation. So this will be the function on which we perform the interpolation. The ideas are very similar. Now, instead of having a linear function between data points, I say I have polynomials. That could be terms with x to the power of 2 and 3 and 4 and so on. There are special names for some interpolations with polynomials where we indicate the highest order in the name. For example, quadratic some polynomial fit, cubic polynomial fit, and so on. So far, so good. Everything's still working? Yes, very nice. Okay, how do we easily define some polynomials now? Let's see. So I see at the bottom is that we are going to use here from NumPy polynomials P. Maybe this part could be here as a reminder. Not the comma there. Comma comes here. There we go. So you can add more and